Welcome to 3D Online Tuition. It is a three-dimensional e-learning method based on audio, visual, and event.
Yippee! Yay!
Chapter 7. Heat. 7.1. Heat as a form of energy. 7.2. The effects of heat flow on matter. 7.3. Effects of heat on matter. 7.4. Application of expansion and contraction of matter. 7.5. Absorbing and giving out heat. 7.6. The benefits of heat flow. 7.1. Heat as a form of energy. 1. Heat, or thermal energy, is the form of energy. It has the ability to do work. 2. Heat can be transferred from one place to another by three methods. Conduction in solids. Convection of fluids, liquids or gases. Radiation, through anything that will allow radiation to pass, including vacuum and space. Solids are better conductor of heat than liquids, and liquids are better conductor of heat than gases. 3. The Sun is the primary source of heat energy to our planet. The heat energy of the Sun reached Earth by radiation only, because there is no medium, like the gas in our atmosphere, in space. Radiation is the primary way that heat travels in space. 4. Beside the Sun, there are other sources of heat. Other heat energy sources. Any form of burning shall produce heat. Any hot objects shall give out heat. Chemical reaction can produce heat. Electricity can use to produce heat. Friction can produce heat. Uses of heat in daily life. Heat from the sun. Drying wet clothes, preserving foods, harvesting salt from sea water, hot water by solar heater, drying agricultural products such as tea leaves, tobacco, cocoa beans, etc. Heat from burning. Boiling water and cooking foods, steam production in power plant. Heat from electricity. Boiling water and cooking foods, ironing clothes, toasting bread. Heat and temperature. Heat. Heat is a form of energy. Heat energy is measuring in joule, J. An object becomes hot when it absorbs heat. An object cools down when it loses heat. Heat flows from a region with higher temperature to a region of lower temperature. The heat content of an object depends on A. Its mass, B. Its temperature, C. The material of the object. Temperature. Temperature is measuring the degree of hotness or coldness of an object. A hotter object has higher temperature than a cooler object. Temperature is measured by a thermometer. Temperature normally measure in Celsius, degree C, or Kelvin, K. Heat and temperature are related, but they are not similar. What is the total heat energy for beaker A and beaker B, if both at the same temperature? Beaker A has 2 times the heat energy to the beaker B, although both are at the same temperature. This is because the total heat energy depends on the mass of the object. When a beaker contains water, is heated by Bunsen burner. Its temperature at the different time is recorded as in the table here. Temperature of an object is depends on the total heat energy it absorbs, or loses. In the experiment above, more heat energy the water absorbs, higher its temperature. Experiments show that the difference between heat and temperature. 1.
Procedure.
1. Fills up beaker A and beaker B each with 200 milliliters of water at room temperature. 2. Measures and records the initial temperature of the water in the beaker A and beaker B with a thermometer. 3. Adds 100 milliliters boiling water into beaker A. Stirs the mixed water in the beaker gently with a glass rod and records the new water temperature. 4. Repeats the step 3 with 200 milliliters of boiling water adds into beaker B. Records the new water temperature. 5. Compares the two new recorded water temperatures of beaker A and beaker B.
Observation.
1. The new water temperature in the beaker A is lower than the new temperature of beaker B.
Discussion.
1. The heat energy in the 100 milliliters and 200 milliliters of boiling water were distributed evenly to the water in beaker A and beaker B, and make the temperature of the water in beaker A and beaker B increased. 2. The volume of the boiling water added into the beaker B was twice the volume of boiling water added into the beaker A. 3. 200 milliliters boiling water provide more heat energy than 100 milliliters of boiling water, based on the higher new temperature in beaker B than beaker A, although both were at the same temperature before the experiment.
Conclusion.
1. Heat and temperature are not similar. Heat energy depends on the mass of the object. Bigger the mass, higher the heat energy it contains, although at a same temperature. Experiments show that the difference between heat and temperature. 2.
Procedure.
1. Set up apparatus as above, with 2 blocks of iron, weighing 50 grams, and 100 grams respectively, put inside a beaker of 50 milliliters of water. 2. Light up the Bunsen burner, and heat up the water until it start boiling. 3. Prepare 2 beakers of C and D, and fill it with 50 milliliters water at room temperature respectively. Record the initial temperature of the water in beaker C and beaker D. 4. Transfer the 50 grams iron block into beaker C, and 100 grams iron block into beaker D. 5. Record the highest temperature reached of the water in beaker C and beaker D. 6. Compares the two new recorded water temperatures of beaker C and beaker D.
Observation.
1. The new water temperature in the beaker D is higher than the new temperature of beaker C.
Discussion.
1. The heat energy received by the iron blocks while in the boiling water were transferred to the water in beaker C and beaker D, and make their temperature increased. 2. The mass of the iron block transferred into the beaker D was twice the mass of the iron block transferred into the beaker C. 3. 100 grams iron block provide more heat energy than 50 grams iron block, based on the higher new temperature in beaker D than beaker C, although both were at the same temperature before transferred.
Conclusion.
1. Heat and temperature are not similar. Heat energy depends on the mass of the object. Bigger the mass, higher the heat energy it contains, although at a same temperature. 7.2. The effects of heat flow on matter. Expansion and contraction of matter. 1. Expansion. The increase in size or volume when matter is heated. 2. Contraction. The decrease in size or volume when matter is cooled. 3. Different matter, solids, liquids, and gases, expand at different rates when they are heated to the similar temperature. 4. When a bimetallic strip, for example brass and steel, is heated, it bends with the metal, brass, that expands more on the outside. When it cooled, it bends on the inside. In solid, atoms, or molecules are close to each other, and vibrates on its own position, at all temperature. When temperature increases, the atoms, or molecules has more energy, and vibrates even stronger, and push the atoms, or molecules next to it further apart. This shall increases the volume, or size of the solid. When solid cool down, it release energy, and the atoms or molecules vibrates less, and the space between them also decreases. This will make the solids shrink in volume, or size. In liquid, atoms, or molecules are close to each other, and vibrates, and moves around randomly, at all temperature. When temperature increases, the atoms, or molecules has more energy, and vibrates even stronger, moving around even faster, and further. This shall increases the volume of the liquid. When liquid cool down, it release energy, and the atoms, or molecules vibrates less, and moving slower, and let it distance. This will make the liquid shrink in volume. In gases, atoms, or molecules are far away from each other, and vibrates, and moves around randomly, at all temperature. When temperature increases, the atoms, or molecules has more energy, and vibrates even stronger, moving around even faster, and further. This shall increases the volume of the gases. When gases cool down, it release energy, and the atoms, or molecules vibrates less, and moving slower, and let it distance. This will make the gases shrink in volume. Experiment to show the expansion and contraction of matter. Expansion and contraction of solid.
Procedure.
1. At room temperature, the metal ball is able to pass through the metal ring. 2. Heat up the metal ball with Bunsen burner for 5 minutes. 3. Let the ball pass through the ring again. 4. Pour some cool water over the heated metal ball to cool it down. Repeat step 3 again.
Observation.
1. After heated up, the metal ball is not able to pass through the metal ring. 2. After cooled down with cool water, the metal ball is able to pass through the metal ring again. Expansion and contraction of liquids.
Procedure.
1. Fill up a flat-bottomed flask with color water near to full. Close the flask with a one-hole stopper with a glass tube. 2. The color water will rise up inside the glass tube. Mark the initial level position of the color water in the glass tube. 3. Put the flask inside a beaker filled with hot water. Mark the final level position of the color water inside the glass tube. 4. Repeat step 3, with flask put inside a beaker filled with ice water.
Observation.
1. When the flask was inside the beaker of hot water, the color water level rose higher than the initial marking on the glass tube, indicated liquid expansion. 2. When the flask was inside the beaker of ice water, the color water level fell lower than the initial marking on the glass tube, indicated liquid contraction. Expansion and contraction of gases.
Procedure.
1. Clips a round-bottomed flask to a retort stand. Close the flask with a one-hole stopper with a glass tube. 2. Insert a small color water column into the glass tube, and mark its position in the glass tube as an initial marking position. 3. Rubs your palms together until you feels the warmest on your hands. Later, hold the round-bottomed part of the flask with your warmed palms. Observes and records the final color water column position inside the glass tube. 4. Remove your palms from the flask. Later, observes and records the final color water column position inside the glass tube.
Observation.
1. When the flask was held by warmed palms, the color water column rose higher than the initial marking on the glass tube, indicated gases expansion. 2. When the palms removed from the flask, the color water column fell lower than the initial marking on the glass tube, indicated gases contraction. Heat flow. 1. Heat energy travel from an area of high temperature to an area of low temperature. When an object come into contact with another object, heat energy will flow from the hot object to the colder object. The temperature of the hotter object falls, while the temperature of the colder object rises, until both objects are of the same temperature. 2. The rate of heat transfer is the difference in temperature between two objects. The greater the difference in temperature, the faster heat flows. 3. There are 3 ways heat transferred. Conduction. Heat transfer in solids. Convection. Heat transfer in fluids, including liquids and gases. Radiation. Heat transfer in vacuum. Conduction. 1. Conduction is the flow of heat energy through solids. 2. When one end of a metal rod is heated up, heat energy travels from one particle to another, from the heated end to the cooler end. 3. Different materials conduct heat at the different rates. Metals are good conductors of heat, for example copper, iron, aluminium and silver. Non-metals are poor conductors of heat, usually called heat insulator or thermal insulator, for example air, glass, wood, plastic and rubber. 4. A metal is feeling cooler than wood, although both are at the same temperature, because metal can transfer heat better than wood. Experiments show that heat flows through solids by conduction.
Procedure.
1. Set up apparatus as above, with a copper rod clamped onto the retort stand, and supported by a wooden block. 2. 4 drawing pins to be stick onto the copper rod, using melted wax. 3. Heat up the copper rod, by placing a flaming Bunsen burner at the end of the rod. 4. Record the time for the pin P1 to P4 to fall from the copper rod.
Observation.
1. Drawing pin P1 fell first, followed by pin P2, P3, and lastly, pin P4.
Discussion.
1. Heat from the flaming Bunsen burner traveled along the copper rod, and melted the wax attached with a drawing pin. The heat reached pin P1 first, which is nearest to the source of heat energy, followed by pin P2, P3, and P4.
Conclusion.
1. Conduction is the flow of heat energy through solids, from the hot end zone to the cold end zone of the solid. Convection. 1. Convection is the flow of heat energy through fluids, including liquids and gases. 2. When liquids or gases are heated up, their hot particles moves faster, and occupy the space of cooler particles. 3. Examples of convection. Boiling water. Water particles at the bottom receives heat energy and become hot, and moves up to replace cold water particles at the top. Breeze. In daytime, the air on land surface becomes hot, and rises up. The colder air blows from the sea to replace it, and causes sea breeze. At night the process is reverse, with the colder air on the land blow to warmer sea as land breeze. 4. Convection cannot happen in solids, because its particles cannot flow freely. Experiment to show that heat flows through liquids and gases by convection.
Procedure.
Convection in water. 1. Put a small crystals of purple potassium manganate, 7, into a beaker full of water, and later heat up the water slowly using Bunsen burner. Convection in air. 1. Put a piece of cardboard inside a gas jar. That will divide the gas jar into 2 compartments. Allow a small gap at the bottom of the gas jar. Place a candle into one of the compartments, and light it up. Put a glowing wooden splinter near another compartment.
Observation.
Convection in water. 1. Purple streams of water moved up and down in a circular motion inside the beaker of water. Convection in air. 1. Smoke from the glowing wooden splinter moved down in the compartment and exit from another compartment with the burning candle.
Discussion.
1. Convection current occurred when particles with higher heat energy in the water and air move to replace particles that are less heat energy.
Conclusion.
1. Convection is the flow of heat energy through fluids, liquids and gases, from the hotter part to the colder part of the fluids.
Radiation.
1. Radiation is the flow of heat energy that does not require a medium. 2. Radiation allows heat energy traveled through vacuum. Heat from the sun is traveled through the vacuum of space to reach us on Earth. 3. The properties of heat energy through radiation are: travel in electromagnetic wave, travel in speed of light, travel in straight line, travel in vacuum, can be absorbed or reflected. 4. Any hot object can transmit heat in radiation form, beside conduction or convection method. 5. The hotter the object is, the more heat energy it can transmitted through radiation. Experiment to show that heat flows through vacuum by radiation.
Procedure.
1. Set up apparatus as above, with electric light bulb put inside an airtight bell jar. 2. Switch on the electric bulb. After about 3 minutes, feels the temperature of the outer surface of the bell jar with your hand. 3. Cool down the bell jar for a few minutes. Turn on the vacuum pump to suck out all the air in the bell jar. After about 5 minutes, repeat step 2 again.
Observation.
1. The hand felt hot when touched the bell jar, while the bell jar was still full of air. 2. The hand felt hot too when touched the bell jar, after the bell jar had become vacuum with all the air inside been sucked out.
Discussion.
1. When the bell jar was full of air, the electric light bulb transferred its heat energy to the bell jar by convection and radiation. 2. When the bell jar has become vacuum, the electric light bulb transferred its heat energy to the bell jar by radiation only.
Conclusion.
1. Heat energy can flow through a vacuum via radiation. Heat flow in natural phenomena. Sea breeze. During daytime, both the land and the sea absorbs heat from the sun. However, the land heats up faster than the sea. The land becomes warm, and the sea becomes cool. The air above the land is heated up by the warm land, and rises up. The air above the sea is considered cooler, and moved toward the land, to replace the warm air that rose up. This movement of cool air from the sea to the land is called sea breeze. Land breeze. During night time, the land cools down faster than the sea. The land becomes cool, and the sea becomes warm. The air above the sea is heated up by the warm sea, and rises up. The air above the land is considered cooler, and moves toward the sea to replace the warm air that rose up. This movement of cool air from the land to the sea is called land breeze. Keeping a house cool and ventilated. Convection currents are used to keep a house cool and ventilated. The hot air inside a house rises up to the ceiling and escapes through the ventilation holes near the roof of the house. Cool air enters the house through windows to replace the hot air that were escaped from the house. The house can keep its cool with such convection current. Warming of the earth by the sun. The heat from the sun travels 150 million kilometers in the vacuum of space to reach our planet Earth. The heat energy of the sun travels in the form of radiation. When the heat energy reaches the Earth, some energy reflected by the Earth's atmosphere, clouds, and Earth itself. The remaining heat energy absorbed by the atmosphere, clouds, lands and seas. There are some heat energy reflected by the surface of Earth, reflected back by the cloud multiple times. The heat energy absorbed by the Earth, atmosphere, and cloud had keeping our planet warm. Heat conductors and heat insulators. Conductors. 1. A conductor is an object, or type of material, that allows heat to flow through it easily. 2. A good heat conductor becomes hot, or cold very fast. 3. Metals are generally a very good conductor of heat, because of the close packing of its particles that allow vibration from one particle pass through to the next particle easily. 4. Example of conductors of heat are copper, silver, iron, aluminium, zinc, mercury, etc. Uses of heat conductors in everyday life. Cooking utensils. Made from steel or aluminium for faster heat transfer from the source of heat to the foods. Soldering iron. Made from copper, for rapidly achieves maximum heat transfer. Electrical appliances. Made from steel, aluminium, or iron, for good heat transfer to the foods. Insulators. 1. Insulators, or poor heat conductors, is an object, or type of material, that do not allows heat to flow through it easily. 2. A good heat insulator becomes hot, or cold very slowly. 3. Non-metals are generally a very good insulator of heat. Vacuum is the best insulator of heat. 4. Example of insulators of heat are air, water, glass, cotton, asbestos, plastic, rubber, wood, polystyrene, etc. Uses of heat insulators in everyday life. Handles of cooking utensils. Made from wood or plastic to prevent heat from reaching the hand of the user. Woolen blanket. Made from woolen yarn that are able to trap air, and together made a very good insulator of heat, to prevent loss of heat from the body. Sawdust. Waste product from sawmill, that can use to cover ice block, to slow down its melting time. Igloo. Built from ice blocks, by Inuits and Eskimo people to prevent the loss of heat from inside the igloo. Ice is a good insulator. 7.3 Effects of heat on matter. Matter typically exists in one of three states: solid, liquid, or gas. On energy level, gas state is at high energy level, whereas solid state is at low energy level. Melting. When solid such as ice cube is heated, it absorbs heat energy and becomes water, which is in liquid state. The temperature where solid starting to melt is called melting point. Freezing. When liquid such as water is cooled, it released heat energy and becomes ice cube, which is in solid state. The temperature where liquid starting to freeze is called freezing point. Boiling. When liquid such as water is heated, it absorbed heat energy and becomes steam, which is in gaseous state. The temperature where liquid starting to boil is called boiling point. Evaporation. Liquid also can turn into gaseous state without boiling. When particles near the surface of the liquid absorbed heat energy from the surrounding, it has enough energy to escape the attraction of the nearby particles and free to becomes gas. Evaporation takes place at temperature below boiling point. Condensation. When gas such as steam is cooled, it released heat energy and becomes water, which is in liquid state. The temperature where gas starting to condense is called condensation point. Sublimation. Solid can change directly from solid state to gaseous state. When cooled, the gas changes directly back to solid state. 7.4 Application of expansion and contraction of matter. Thermometer. Mercury is used to measure changes in temperature. When surrounding temperature rises, the mercury absorbs heat energy and expands. Mercury column rises. When surrounding temperature falls, the mercury releases heat energy and contracts. Mercury column falls. Fire alarm sensor. Fire alarm sensor is a fire detection and alarm warning device. It has a bimetallic strip that can bend when heated up. During fire incident, the bimetallic strip is heated up by the fire. The bimetallic strip expands and bends. The bimetallic strip touches the contact screw. The alarm bell will sound. Bimetallic thermometer. Bimetallic thermometer, typically used to measure temperature between -65 degrees Celsius to 430 degrees Celsius. It uses the bimetallic strip, which converts the temperature into the mechanical displacement. The bimetallic thermometer was designed to be a less accurate, but as a more rugged measuring device, mainly used in the industrial. The coiled bimetallic strip is made from either steel and copper, or steel and brass. When surrounding temperature rises or falls, copper or brass expands or contracts faster than steel and causes the strip to curl and show the rise or fall in surrounding temperature. The common application of bimetallic thermometer is as temperature gauge in the industrial. However, they are also used in home appliances, such as electric oven, and also in the car radiator, to show the engine's temperature. Electric irons. In an electrical iron, the three major components are: 1. The heating coil, to heat up the irons; 2. The temperature controller, to set the desired temperature; and 3. The bimetallic strip, that bends to cut off the power supply to the heating coil, when the temperature of the iron is over the preset temperature, in the temperature controller. When power turn on, the heating coil's starting to heat up, and the iron becomes hot. When the iron becomes too hot, over the preset temperature, the bimetallic strip expands, and curves upwards. Power cut off. After the power cut off, the iron cooled down, and the bimetallic strip contracts, and returns to its original position. Power returned to the heating coil, and the iron becomes hot again. The bimetallic strip will go through repeated expands and contracts to allow the iron maintain at the preset temperature. Rivets. Rivets are steel bolts used to fasten two metal plates firmly together. Rivet is heated up over a strong flame, or inside an oven. Then it is fitted into the hole connected to two metal plates. Rivet setter is then used to spread the end of the rivet. After the rivet cooled down, it contracts, and holds the two metal plates tightly together. Wheel axles. Axle is cooled by liquid nitrogen at -190 degrees Celsius. The cold axle is inserted into the hub of the gear wheel. After the axle warms up, it expands, and fits the gear wheel tightly. Using the principle of expansion and contraction to solve simple problems. Railway tracks. If a railway track is built continuous for very long distance, without break, it will buckle. When temperature rises, due to no more room for expansion, buckled tracks can cause train to derail. To prevent railway tracks buckled, small gaps are left between section, to allow room for expansion during hot weather. Metal bridges. A metal bridge will damaged, or collapsed during hot weather, or in the cool winter if there is not room for the bridge to expand and contract. To prevent this happen, firstly, the bridge is fixed at one end, and let it have a sliding joint at the other end of the bridge. Under the bridge, few rollers places at one end to allow room for the bridge to freely expands, or contracts. Overhead power cables. During noontime when temperature is hot, the power cables expand and sag. During nighttime when temperature is cool, the power cables contract and tighten. 7.5. Absorbing and giving out heat. 1. All objects are able to absorb and radiate heat energy. However, different objects absorb and radiate heat energy at the different rate. 2. The rate of absorption and radiation of heat by an object depends on A. The temperature around the object. B. The type and color of the object's surface. 3. The hotter an object is, the more heat energy it gives out. The colder an object is, the more heat energy it absorbs. 4. Dull and black objects absorb and radiate heat better. Shiny and white objects absorb and radiate heat lesser. 5. Object absorbs heat from surrounding. Its temperature up. Object gives out heat to the surrounding. Its temperature down. Experiments show that a dull and black surface is better heat absorber than a shiny and white surface.
Hypothesis.
A dull and black surface is a better heat absorber than a shiny and white surface.
Variables.
Manipulated. dull and black surface, or shiny and white surface. Responding. Time taken by the thumbtack A and B to fall. Constant. Size and thickness of metal plates, distances of metal plates from light bulb, size of the wax and thumbtacks used.
Procedure.
1. Prepares an apparatus as shown, with 2 metal plates or same size and thickness. Place the 2 metal plates at the same distance from the light bulb. 2. Attach 2 thumbtack A and B, with wax on the surfaces of the metal plate that are not facing the light bulb. 3. Turn on the light bulb, and record the times for thumbtack A and B, to fall from the metal plates.
Observation.
1. The thumbtack A attached to the metal plate with dull and back surface, fell first.
Discussion.
1. The wax that attached the thumbtack A to the metal plate with dull and black surface melted first, indicated that it received more heat from the light bulb.
Conclusion.
A dull and black surface is a better heat absorber than the shiny and white surface. Hypothesis is accepted. Experiments show that a dull and black surface is better heat radiator than a shiny and white surface.
Hypothesis.
A dull and black surface is a better heat radiator than a shiny and white surface.
Variables.
Manipulated. Dull and black surface, or shiny and white surface. Responding. Temperature of hot water in the glass bottles. Constant. The surface area of the glass bottles, temperature, and volume of hot water.
Procedure.
1. Prepare 2 similar size empty glass bottles. Bottle A paints with dull and black surface on the outer layer of the bottle. Bottle B paints with shiny and white surface. 2. After the paint dried, put the 2 bottles on 2 pieces of asbestos apart. 3. Pour equal volume of hot water into both bottles, and covers it with stopper with a thermometer. 4. Record the initial temperature of the water inside the bottles, and once again after 10 minutes.
Observation.
Bottle A. Initial temperature 90 degrees Celsius. Final temperature 52 degrees Celsius. Bottle B. Initial temperature 90 degrees Celsius. Final temperature 73 degrees Celsius.
Discussion.
Bottle A lost more heat energy than bottle B. It means bottle A radiated more heat to the surrounding than bottle B.
Conclusion.
A dull and black surface is a better heat radiator than the shiny and white surface. Hypothesis is accepted. 7.6. The benefits of heat flow. The transfer of heat, or heat flow by conduction, convection, and radiation, is very important to the human everyday life. Conduction. The good heat transfer in metal through conduction enable metal used as cooking utensils and electric iron. Convection. Convection currents are used to keep a house cool and ventilated. Radiation. The sun heat energy travels in radiation throughout the vacuum of space to reach our planet and help to keep us warm. Expansion and contraction of matter. Electric irons. Rivets. Thermometer. The expansion and contraction of matter provides us with some simple but useful applications to solve our daily problems.
Happy learning